Welcome everyone. You're signed on to the Precision Digital webinar. The title of this one is The Fundamentals of Pulse Inputs. Now, this webinar is designed as a basic course. It's not for advanced electrical engineers, but it's designed for those of you who have to deal with pulse signals out in the field but aren't electrical engineers. If you missed the first series we did on 4 to 20 milliamp loops, current loops, you can still see that series on the Precision Digital website at PREDIG, that's predig.com/webinars. So feel free to check that out. It was very well received and we got a lot of good feedback about it. Some general housekeeping today. Most common question we get from folks who sign on is, will we get a copy of the recording, the recorded version? The answer is yes. Everyone who registered will get a email after the fact with a link to the recording and the slides, and the webinar recording will also be available on the Predig Precision Digital website. Everyone is in a listen-only mode. That means you can't talk to us live, but you can ask a question. And the way you ask a question is to type in the chat box in your lower left-hand screen. Just type your question as it comes to mind. You don't have to wait for the Q&A sessions. Type it in, and when we get to those sessions, we'll be answering questions as they come in. So again, we encourage you to ask questions when it comes to mind. Again, this webinar is being recorded, and the recording will be available to all who register via email and via the website. This webinar is presented and produced by Precision Digital Corporation. Precision Digital designs, develops, and manufactures a full line of digital panel meters and associated devices. Now, we don't talk about the products during the webinar because this is strictly educational. But naturally, if you have questions about the products, whether it's pulse input meters or so on, please give us a call or shoot us an email. Naturally, we'd be delighted to talk to you about the products. But this webinar is about pulse inputs, and it's educational. Speaking today, my name is Bruce McDuffie. That's me on the left there on the screen. I'm with the Precision Digital Corporation marketing team, and I'll be your moderator today. Behind the scenes, Ryan Shea is working to answer your questions in the chat window. Ryan is an application specialist with Precision Digital Corp. He answers all incoming phone calls about signals and pulse inputs and 4 to 20. So it's likely if you call into Precision Digital, you'll hear me talking to Ryan. Ryan's calling in from the Precision Digital headquarters in Holliston, Mass. Your main speaker today is Joe Ryan. Joe is the product manager with Precision Digital. He brings 10 plus years of process signal experience in design, support, manufacturing, and marketing of all types of process measurement and control devices. Joe has extensive field and support experience in pulse signals, pulse inputs. And with that introduction, I'll turn it over to Joe to kick it off. Joe?
All right. Well, thank you very much, Bruce. First, why don't we take a look at what the agenda of today is and really what our objectives of this webinar are and what we hope that you, the audience, will have as takeaways from this. The first thing we want to do is give you a basic understanding of the theory behind what process pulse signals are. In general, we found that a lot of people understand signals like 0 to 10 volts or 4 to 20 milliamps, but there's a lot of confusion around pulse signals and what all the terminology means, and we hope to set you on the right path to understanding those a little better. We want you to become familiar with the specifications that describe pulse signals, specifically those key terms that you're going to hear when you have to install a system or specify two pulse devices that are going to need to talk to each other. It's a very different terminology than you would find in other forms of analog controls like 4 to 20 milliamps. There will be a brief discussion about the pros and cons of pulse signals. There are reasons why pulse signals are used. There's definite advantages to them, but they bring with them a set of cons that you have to be aware of if you're going to work with these sorts of devices. And then we've got a couple examples at the end that show you real-world applications. situations where it makes sense to use pulse signals and they could be successfully installed in the field in order to give you a sense of when you might run into these kinds of devices and really what those strengths are that make them the superior choice. But before we dive into the nitty-gritty detail, Bruce, you had a few questions.
Yeah, it's always fun to kind of get to know who's out there in the audience. We've got a couple of hundred people out there today. It's fun for us and helpful for us, and it's usually helpful for the audience to know who else is out there, location, industry, and so on. So the first question is, where are you located? Everyone can just choose the region by just clicking on the poll, and we'll show the results as they come in. Give it a few seconds here for everyone who wants to vote. The last webinar we had most folks were from the eastern U.S., so looks like Central is, oh, here comes Eastern. Give it a few more seconds for everyone to vote who wants to. Looks like Central U.S., biggest participants this webinar. Okay, go ahead and close the poll. Last chance. Okay. And there's the results. Central first, Eastern next, Western Canada, and almost 5% from other. Okay, next poll. What is your industry? What industry are you from? And these are, you can only pick one. So go ahead and vote. Take a look at the results as they come in. Coming in fast and furious. Industrial distributor, by far the biggest participants today. Good mix from manufacturing, utilities, consulting, and still 10% other. You get a chance, if you chose other, if you could type in what other industry is, that's helpful for us. Type it into the chat window. Okay, good. Last chance. Closing the poll. There we have it. Good mix. It's always good to have a good mix. That helps us with understanding how to tailor the content a little bit. Okay, and one last poll before we get into the meat. This helps Joe when he presents to know what kind of experience is out there. So what is your expertise with pulse devices? Are you an expert? You just know enough to get the job done, a novice, or this may be the first time you've heard of pulse signals? Pretty good. Nearly a quarter. It's the first introduction to pulse. Looks like we have a couple of experts out there. Always good. Okay, everyone vote who wants to. Closing out the poll, and there's the results. Good, another good mix. I'm a little surprised about the contingent who's never heard of pulse or this first introduction. But that's good. That's what this is designed for, is really the basics. Okay, Joe, let's kick it off with theory, terms, and definitions. It's all yours.
Thank you, Bruce. For those of you who appear to be most of you who either have never really been exposed to this topic before or who know enough to cobble together a solution in the field when you're called on to do so, which covers apparently the vast majority of you in the audience, I think you'll find that we'll take it kind of slow on the theory, terms, and definitions and try to make you leave here with a pretty good understanding of what all of this actually means. So thanks for joining us. So the first question then is, what is a pulse signal? What does it mean when somebody says, well, I've got a pulse output, or this device is going to take a pulse input? Well, it means something very different than your more traditional forms of 4 to 20 or 0 to 10 volt analog signals. A pulse is a two-wire signal, and those two wires, out of that, you're going to be able to read an off or an on state at any point in time. Now that statement's very important, because if you think about it compared to, say, a two-wire 4 to 20, a 4 to 20 milliamp signal, you could have 4 milliamps, 6 milliamps, 12.5, 16 3/4 milliamps. There's an infinite range that you could read off those two wires at any given point in time, anything between 4 and 20 milliamps. But a pulse signal is specifically always either on or off. And that's really why you use a pulse signal. That is the characteristic that makes this such a unique signal for process control or measurement. The way you send your value then is the number of on voltage pulses that you pick up on that line and how fast those pulses are coming in or being generated. That's how you're going to read your process variable. How many pulses did I get over a specific period of time is going to equate to your value. So for example, you're going to be sending out more and faster pulses as your flow rate increases. As your flow rate decreases, that same flow meter is going to reduce the speed at which it's sending pulses. And as I was mentioning before, unlike a 4 to 20 milliamp signal, the pulse signal is always either on or off at a point in time. It's all about changing the state of that line quickly, generating more and more voltage pulses as your process variable goes up. And to give you a sense of scope, these changes are going to be happening very quickly. So you may get a pulse on and then off in the range of 0.1 milliseconds or faster. You're going to see numbers being thrown around like 30 kilohertz, which means 30,000 pulses per second. So these pulses are really moving much faster than you could perceive it visually if such a thing were possible. But the electronics, of course, can handle those kinds of speeds. But just so you have an understanding of how quick they're going extremely fast. So let's look at what a pulse signal actually is. What you see here on the screen is the ideal pulse signal. You're very rarely going to run into this in the field. But for the purposes of defining the terminology, let's start with this. What you see here is a square wave, meaning it's got sharp on and off voltage transitions. You're usually somewhere down at 0 volts, and that's going to be considered to be your off state. And that would mean that here, for example, I would have 0 volts. And then something's going to happen in the electronics, and it's going to register a pulse, and it's going to generate for me a 5-volt transition. Now, I put 5 volts here. That realistically could be, for the purposes of an ideal signal, that might be 24 volts. But in the ideal world, I've got a nice high voltage signal like that that's very noise immune and is a very sharp transition. The amplitude, which is a term you're going to hear, is going to be the height or the voltage level of the signal. So in this case, the amplitude of my square wave is going to be 5 volts. So it's going to be from the low signal to the high signal. That's my amplitude. The period of the pulse signal is the time it takes for one on-off cycle. So you can see that illustrated at the top just above the pulses, where you've got the combination of the time the signal is high plus the time the signal is low before the next pulse comes along, and that represents my period. Lastly, probably the most common terminology or definition you're going to run into is frequency. Frequency is the number of on-off cycles per second. So how long is it between having the pulse start to go high to another pulse starting to go high? And that's the value where you're going to hear it defined in terms of 30 kilohertz, 10 kilohertz, a couple of hundred hertz. And I'll talk a little bit about what hertz means in a minute. But frequency is generally defined in hertz, and it's the number of pulses you're going to get per second. Now, unfortunately, in the real world, you don't generally get those nice sharp transitions, and you'll often run into situations where you don't have very strong voltage pulses in the 5+ volt range. Luckily, any type of waveform can actually be used, any type of waveform can actually be used to generate a pulse signal, even something that isn't so clearly delineated like a square wave with, okay, that's where I go high and that's where I go low. What you see here on the screen is the type of waveform you might have generated out of a magnetic coil pickup flow meter. You can see it's not a square wave, it's an AC sine wave. But the electronics in pulse devices are capable of turning this into something that can be read out as pulses. And the way it does that is with thresholds. So in this case, you're going to have an upper threshold, and you're going to have a lower threshold. And the threshold is a voltage level. And what that says is that anytime my voltage gets above a certain point, I'm going to consider that to be a high. And anytime my voltage gets below a certain point, I'm going to consider that to be a low. To give you a sense of scale, I included here the thresholds for our PD6830 flow totalizer. So for a normal active pulse, meaning that it's a powered pulse coming out of something that's likely externally powered, I'm going to have a normal setting for thresholds that gives me a low of 1.2 volts, meaning anything below 1.2 is going to be considered a low, and a high of 2.0, meaning anything above a 2 is going to be considered a high. So if I were to look at that waveform at the top, I'm going to figure out what my thresholds are, and I'm going to say, well, you know what, anything above this value is going to be considered to be a high. So I'm going to have a high here, I'm going to have a high here, I'm going to have a high here. And usually because of the way these work, I'm also going to say, well, I probably have one there, and one there, and one there. So even though I don't have a nice square wave here, I do have something that I can fairly easily convert into a pulse signal. And then again, I just start counting those peaks, saying, okay, how many of these pulses do I have coming in a second? That's going to be how I map it over to what my process variable is. Oh, and Bruce, a pop quiz.
Yeah, we're going to have quizzes on this webinar, so I hope everyone's been paying attention. We're not going to have too many, but a couple. So this first pop quiz, a pulse signal is characterized by which one of these choices? As Joe just went over this in the last few slides. I'm not going to show the results as they come in so as not to prejudice the answers. But answers are coming in. So keep them coming. I'll give it a couple more seconds for folks to vote, or answer, rather. Okay. Last chance. And here are the results. Looks like the answer, 91% say a signal that is on or off. Joe, is that right? Oops, Joe.
Sorry about that. That's correct. All pulse systems are based around the idea that at any point in time, you've got an on or an off state. And even though you may actually have some kind of a sine wave there, or a sawtooth wave, or a strange shape, you're always going to say it's either on or off and count the number of times it turns on.
Okay. Good job, everyone. Joe, back to you.
All right. So now that we have an idea of what that pulse looks like, that it's some kind of voltage that's being generated and cycled, how does that get generated? Well, there's a number of different types of pulse output flow meters that can generate pulses. And those are probably the things that I'm guessing this audience is most familiar with. There are a few others as well, and we'll touch on those in a bit. Some of those common flow meter types are positive displacement or turbine meters. And if we look at those, it gives you a fairly good idea of how this pulse is generated and why you're able to use it in order to get your process variable out of your system. The key there is that a pulse is always going to represent some specific amount of your process variable. So in the case of a flow meter, you're going to know that every pulse is going to have a certain amount of flow associated with it. Or if you flip that around, you're going to know that 1 gallon of liquid is going to equal some number of pulses out from your flow meter. All those other types of technologies that are out there, like rotary encoders and linear measurement devices, all function on basically the same concept here, that 1 pulse is going to equate to 1 amount of rotation on my rotary encoder, or that 1 pulse is going to equal a certain amount of feet traveled on a conveyor belt. Let's take a closer look at how that might happen. What you see here is a positive displacement meter. And I could give an entire webinar on the functions of each individual type of flow meter, but that's not what we're here for today. Mostly what I wanted to point out was how these operate in terms of generating pulses. So in this example, what you've got is a certain amount of liquid is going to enter this oval gear system. And that liquid is going to travel through it in such a way that there's no way for additional liquid to get through without being metered, and there's no way that it's going to rotate through with, say, an air bubble in it, or ideally anyway, some other liquid or material that could be faking that a pulse exists. So in other words, if I'm going to pass through this volume of liquid, whatever that volume is, it's going to be rotated through with the oval gears. And when it comes out the other side, I know that now I've had some type of rotation on this gear. So as this gear rotates, it's passing through a specific volume of liquid. Pulses are most easy to generate off of rotating equipment, usually by using magnetic pickups. So I can generate pulses as this gear spins, knowing that it's let through a specific discrete amount of liquid for that number of pulses that I managed to generate. You can apply that same type of concept to a turbine meter. Now a turbine meter isn't going to have the oval gears and isn't going to only allow material to pass through at a certain rate. However, the rotor inside of the turbine meter, the blades are going to spin at a certain rate as determined by how much liquid is being passed through. So as I use a pickup to sense the rotation of that rotor of the blades, I'm going to be able to say, well, based on how fast that's spinning, based on how fast my pulses are coming out, I can tell you how much flow is going through that pipe, because I'm using rotating equipment that has a pickup on it to generate a pulse output based purely on the mechanical setup here. There's a way that the flow meter manufacturer has determined that will say, you know what, if you put through this much liquid or you put through that much liquid, this is the rate the pulses are going to be getting generated at. So what are some common pulse generating device characteristics? Well, in both cases, one pulse is going to be able to equal a specific value. It's going to either represent a certain volume of material pushed through my system, or a certain flow rate, or a distance amount traveled. They're often generated by rotating equipment. That's the place where you're going to see pulse generators the most. Again, you go back to rotary encoders, flow meters, those sorts of devices where if you think about how they're working, you can imagine something spinning inside that's generating a pulse as it spins. Oftentimes these require little to no power. Because it's a mechanical form of measurement in most cases, the mechanics take care of spinning the rotor or moving the gears or turning the rotary encoder disc. And as a result, you don't need the kind of power you would need for, say, an ultrasonic level transmitter that's generating a 4 to 20 milliamp output. So pulse devices are great in that they're very low power solutions to problems, and we'll see how that can be used to your advantage later. And usually these get connected to a register or a meter, which counts and interprets the pulses. So it counts the pulses as they're coming in, and it tracks the rate that the pulses are coming in to get the process variable. And oftentimes that register is then going to retransmit that value somewhere else. There are reasons which we'll cover in the pros and cons about why you can't send pulses long distances, but usually if you're going to be sending this back to a control room or some other piece of remote equipment, you're going to want to convert it over into a 4 to 20 milliamp signal. So oftentimes your register would be the thing to do that. You would have something like you see in the picture here, a register or totalizer mounted directly on the flow meter, and then if you wanted to, you could have a 4 to 20 milliamp line just coming out of this and going off to your control room. And pop quiz for you.
Pop quiz number 2. Which of the following are devices that generate a pulse signal? You can choose all of the devices in this list that will generate a pulse signal, or none of these. And I am not going to show the results until everyone has voted. So go ahead and vote, and you won't see any activity on the screen right now. The votes are coming in. Which of the following are devices that generate a pulse signal? Coming in good. Please keep voting. Choose all of them that apply. As a reminder to everybody, if you have questions coming to mind, go ahead and type your questions into the chat window. We have a Q&A session coming up here in a few slides. Well, there is activity on the screen. Somebody said there's not supposed to be.
Looks like we'll just be on the honor system here.
Yeah. Maybe that's why we had 91% on the last quiz. Yeah, it's not supposed to be. I'll check into that. Apologies. I didn't know that it showed the results as they came in. So let's go ahead and close out the poll. And here's the results. Looks like, for the most part, positive displacement meter and turbine meter. A few people like the Johnson cubic meter. That's my favorite. I made that up. Joe, any comments on the quiz?
No, I'm pretty happy with the results. Hopefully that means people understand that that rotating type of equipment that we were talking about is where you're going to see pulses.
Yeah. Okay, back to you, Joe.
All right. So why don't we talk for a moment about a couple of the key specifications that you're going to have to understand if you're going to work with pulse equipment. And the one that is likely to come up the most is going to be maximum frequency. So as I mentioned earlier, frequency is the speed that your signal is running at. It's the rate at which pulses are getting generated or coming down your line. It's measured in hertz, although you often see it as kilohertz or thousands of hertz. And it's how many pulses per second is being sent. So your maximum frequency on a device is the maximum number of pulses per second that your device is going to be capable of handling. So on a pulse generator like a flow meter, it's going to be the maximum pulse output frequency. On a register or a totalizer, it's going to be the maximum input pulse frequency. And these are generally going to be at very fast speeds. You're going to see numbers like 10, 30, 60 kilohertz. Those are not uncommon values to see. What's important here is that you need to make sure that the pulse generator is not going to be generating pulses at a higher frequency or at a faster rate than your pulse receiver, your register, your totalizer, whatever you're connecting it up to, is going to be able to receive those pulses. So if I have a flow meter that maxes out at 60 kilohertz at its highest flow rates, and I'm connecting that up to a pulse register to read the total that goes through that flow meter, but my register can only handle 10 kilohertz, I have a problem on my hands. So you need to be aware of what the maximum frequency is for your devices so you can make sure that the generator's maximum frequency is equal to or lower than your receiver's maximum frequency. Otherwise, you're going to have all kinds of strange behavior, from maxing out and just showing your maximum value for everything that's over, or you could even start getting some kind of strange aliasing going on where the results will be unpredictable. The other key specification you need to understand are the voltage peak and threshold of your devices. So the pulse receiver needs to be able to pick up the voltage range being generated by the pulse generator. And that really has to do with that pulse amplitude concept. The amplitude being the height of the voltage pulse being generated. The pulse generator is going to have some kind of a specification to it that says what its voltage peak is for its pulse, or what its voltage peak to peak is for its pulse. And your pulse receiver is going to have either a specification that says we work with pulse generators that have this value as their amplitude, or it's going to say what its thresholds are, which are the levels at which it can see a high and a low. And you need to make sure that those values are going to be compatible. If I'm using a pulse generator that puts out a 3-volt maximum pulse, but I'm using a pulse receiver that has a high threshold of 4.5, well, my pulse generator's 3 volts is never going to reach the 4.5 volts that my pulse receiver is looking for in order to register the high. And so I'm never going to pick up anything being generated. The time when that comes in, or the time that that's likely to come up the most, is on magnetic pickup meters, usually magnetic pickup flow meters. Those generate very low voltage pulses. We're not talking volts, we're talking millivolts in most cases. You could have a mag pickup flow meter that's putting out 40 millivolts or 30 millivolts or even down to 10 millivolts peak to peak. So you need to have a very sensitive receiver to pair with that. Otherwise, that receiver could be looking for a 2-volt pulse signal, and your 20 millivolt peak-to-peak flow meter is never going to get anywhere close to that. So when you know you're working with a device that isn't powered, like a mag pickup flow meter, then you have to be aware you may be talking a very low voltage peak, and you're going to need to make sure that your pulse receiver is capable of reading that signal. That its voltage thresholds are low enough it can pick up those highs. And one more question from you, Bruce.
Yeah, this is a get to know you. This is not a quiz. So the question is, let's see what kind of applications folks are dealing with out there. The question is, what are your primary pulse applications? You can choose multiple choices in this quiz, not quiz, question. And I'm going to show the results on this one. I guess we had an answer from the last question. Folks were seeing the results, and Tristan clued us in. The answer is after you vote on the quiz, you can see everything after that. So you have to commit to your answer first, then you see the results. Makes sense. Thanks, Tristan, for that info. We're learning too on this webinar, Joe.
We are.
The answers are coming in for the applications. Looks like flow, speed, and counting. Give it a couple more seconds. Anyone else want to vote? Now's the time. Okay, I'm going to close the poll now.
Hopefully our flow meter examples then are hitting home, given I saw 91% handle flow.
91% for flow, yeah. Good. Thanks everyone for voting. And now we have some questions and answers we're going to take, and this is not the end of the presentation, so don't bail out now. We've got a lot of good info coming up still, but let's break for some questions. Joe, the first question we have is from Robert. Robert would like to know, would shielded cable be required for pulse wiring?
Obviously, I'm not going to say it's absolutely required or the signal won't work, but it is one of the smartest things you can do. Pulse signals are notorious for their ability to pick up noise. Because the pulses are often very low voltage in amplitude, if you get a lot of noise on that line, your pulse receiver is not going to be able to tell the difference between a pulse that was generated properly or a noise spike that comes through. And it's going to register that noisy situation as a whole lot of pulses potentially. So anything you can do to reduce noise in your system, like using shielded cable, is really an absolute must if you need good, accurate systems somewhere where you might have noise able to be picked up by your connecting wire. Do we have another one?
Yeah, Joe, we have a question from Henry. Henry's question is, what types of devices are typically receivers?
Well, there's two types of things, or two categories I would say you usually see the receivers fall into. The first is going to be your field instrumentation. That's going to be something that usually has a display on it, and it's something that someone's going to be interacting with a lot. So you're going to have like a counter with a total going on it, or you're going to have a flow meter that's displaying a rate value. The other type of equipment you're going to see is basically just a signal converter. And that would be something that, like a preamp, that just takes in the pulses and immediately converts it onto a 4 to 20 to retransmit that value to somewhere like the control room. They both are essentially the same device. They're all just receiving in pulses. It's just a question of, are those devices then displaying it, making it available to operators? Like, is it a batch controller where the operator needs to interact with it? Or is it just going to be receiving that value to retransmit it off to some other place in your control system? But in all those cases, you're going to find that you're best off not running pulses a long distance, and I'll talk on that in a bit. So you usually have something located fairly close to the generator to receive that pulse signal and either act on it right there locally or send it off to somewhere else to be acted on as a different type of signal. Next.
Okay. Got a question from Colin, who's asking, is there a minimum frequency? This is a two-part question. Is there a minimum frequency, and can zero-based applications use pulse technology?
Zero-based applications certainly can. So let me start there. But it's going to depend on the application and the type of device you have generating your pulses. If I have, for example, a rotary encoder that's measuring speed, I can probably handle zero applications there well, because if I have zero speed, my encoder's not moving, I'm not generating any pulses. However, there's flow meters, for example, that do recommend minimum amounts of flow in order to maintain their accuracy. And so depending on the quality and technology in your device there, they may only hold to their accuracy specifications above a certain flow rate. So it is recommended, if you think you're going to be handling very low flow, that you get a flow meter that is geared towards your flow level. And don't just assume, well, I've got something that can handle 10 times the flow I need, I'm going to be A-OK. You really want to look at those specs, check the accuracy specs, and see if they've got a minimum flow rate they stand behind before the flow meter might start getting nonlinear or start missing or reporting extra pulses. Do we want to handle another one now?
Yeah, I think we can handle a few more. We're in good shape time-wise.
Okay.
Peter has a question. Can this apply to gases to measure the flow rates? I guess it means can you measure gas flow rates with this technology?
You absolutely can. Obviously, you need a flow meter that's specifically designed to handle gases. But if you get a gas flow meter, then you can absolutely handle it with pulse outputs. In fact, very often I've seen someone will have a gas flow meter that generates a pulse for the flow rate, but then you have some other kind of sensor as well built in the flow meter if you're doing something like pressure and temperature compensation with a gas. So you might have a pulse output for the flow rate, but then have a thermocoupler and RTD and maybe a 4-to-20 for the pressure. But as a simple answer to your question, yes, there's no reason you can't have a pulse output from a gas flow meter. Okay?
Okay. Let's take one more question. I got one short one and maybe one longer one, and then we can move on. The short one is from Russell. Are pulse signals generally universal or proprietary?
I'm going to answer, unfortunately, with neither. So a pulse signal is not universal. There's really no good standard there for what the amplitudes or maximum frequencies need to be in these devices, which is why it's critical that you recognize those amplitudes, thresholds, and frequencies and be able to match up your device's understanding what those terms mean. But it's also not proprietary. Pulse signals are used by all sorts of manufacturers in all sorts of fields, and the fact that you're changing the frequency of your pulses to increase your process variable, and the fact that there is a amplitude and a voltage threshold on your devices for your pulses, that's all just standard terminology used in this type of process signal. So while there's no good standard to say, well, every pulse device works with every other pulse device like there is with a 4-to-20 milliamp signal, nothing here is really proprietary to any manufacturer. Hopefully that clears that one up.
Okay, and we'll take one more, and then we'll move on. This is from, and I apologize in advance for the first name, I believe it's Giame. Sorry, can't even do it. Question is it grounded like a 4-to-20 milliamp at a single point only?
I would recommend that you probably don't want to ground your the negative side, so to speak, of your pulse signal wire. But if you're using if you're using shielded cable and your device housings are metal as well, then in that kind of circumstance, whenever you're trying to reduce signal noise, I do recommend single point grounds like you would use in a 4-to-20 signal setup, yes. Okay, great questions everyone. Thanks. There's some more we'll cover at the end,
keep them coming, and if we don't happen to get to it during the live broadcast here, we'll get to you after the fact. So keep those great questions coming. And on to pros and cons, Joe.
All right. So we said earlier we'd talk about the pros and cons of pulse signals. So far they might be sounding pretty bulletproof and like hopefully they're pretty easy to work with, but they do bring some cons with them as well. First, let's talk about the pros. So a pulse signal is generally a direct measurement, meaning that you're not taking an ultrasonic level signal and somehow converting that over into a 4 to 20 milliamp where there's a lot of analog conversion going on and a lot of opportunity for inaccuracy. Pulses are directly connected to what's generating them mechanically. So you have very good accuracy on what values being transmitted by a given pulse. If you think back to the turbine, or I'm sorry, the positive displacement meter, there's a very good level of accuracy that says, okay, I'm moving this amount of liquid through my system and it's generating this number of pulses. They could potentially have good noise immunity. Because you just have an on-off state, if I have a nice strong pulse, let's say I have something in the 10 volt pulse range, because I have a pulse generator that's externally powered and I have a powered pulse being generated out of there, and my low is at 0 and my on pulse is at 10 volts, well, that's a nice strong signal, and noise is going to have a hard time impacting that, because even though it may change my 10 volts to 9.8 volts, it's still going to be very easy to pick up the fact that 9.8 volts was clearly meant to be a high, and let's say 0.2 volts was clearly meant to be a low. So if you have a nice strong active pulse signal coming out of that, then it's going to have good noise immunity characteristics. Another pro of pulse generator devices is that no power can be required. There is such a thing as a no power pulse device, and you often see those in rotary encoders and flow meters. Something like the vortex flow meter isn't going to, or I'm sorry, the turbine flow meter we looked at earlier, isn't going to necessarily require power to generate its pulses. It's being generated by a mag pickup in most cases, and so it's purely a mechanical action that's generating my output pulse. It may require power. There's going to likely be versions of that meter that I can hook up 24 volts to get a nice powered pulse output. But if I'm okay with a low amplitude pulse, I don't need to bring power out to the field. And in those cases, you'll often find that pulse devices can be fairly low cost. If you avoid the need for expensive preamps or other expensive kinds of sensing devices, oftentimes basic rotating equipment pulse devices can be pretty cheap on the pulse generator side. Now there's definitely some cons. The devices have to be compatible that you're using in your system. And that's the one that I usually see people have the most difficulty with. You need to make sure that the maximum frequencies match up, that your generator isn't going to be making things faster than your receiver can read. And you need to make sure that the voltage threshold is going to be able to pick up the amplitude of the pulse being generated. If you mismatch those, then your system's going to fail. And if you don't have an understanding of what that terminology means, you're going to make those mistakes. They could be susceptible to noise. Now I know earlier I talked about the fact that they could have good noise immunity, but that was for a pulse generator that's making nice powered, close to ideal pulses. If you actually have one of those no power flow meters and it's generating 20 millivolt peak to peak sine waves, it's going to be very noise susceptible. So in those circumstances, you want to run your wires as very short length as you can, shield them as much as you can, and be aware that noise is going to be a problem for that system. Complexity is definitely a con for pulse meter systems. The fact that you're here speaks to that. This isn't as common as 4 to 20 milliamps is in the process industry, and the terminology is so different that a lot of people just aren't familiar with it. They don't know how to wire them up. They aren't sure what to look for as far as problems go. And so they often are figuring out as they go how these systems have to work. And so you need a little extra training to be able to really understand what's going on in your pulse system. And as I spoke earlier, the signal run distance is limited. It's not that there's particularly any problem with running a signal over a long distance from a voltage perspective. The resistance of wire is very low, and it's going to propagate perfectly fine as far as speed goes. The real problem with running your signals long distance is going to come down to noise. You're basically running a giant antenna if you decide to run a long wire, and that's going to pick up a lot of noise on your system, which is going to cause you problems because your receivers are going to have difficulty reading what is going on with your pulses when there's a noise signal riding on top of it. You run the risk that your highs are going to either be pushed down below the threshold or that false highs are going to be generated, and the same for the low signals. So you really need to be wary of noise, and one of the best ways you can reduce that is to keep your signal very short run distances. So now that we've discussed the pros and cons, let's take a look at some real-world applications that show you where pulse signals can really shine. The first one is on an oil feed line coming out of a storage tank that uses a mag pickup flow meter to totalize everything going through that line to a couple of different filling stations. So in this example, oil in this tank is going to be flowing down this line, pass through my flow totalizer and my flow meter, and then it's going to be divvied out to the different fill stations. But I want to have a sense on my rate totalizer here of what's going on, how much is being pushed out right now in terms of rate, but also how much has been pushed out for the day in terms of total. Now the mag pickup flow meter, which is here, requires no power, which is great because now I don't see anything here that's powered, and I don't need to now run 24-volt cabling out to this hazardous location. I would have to worry about explosion-proof conduits, making sure my 24-volt supply goes through barriers. This way, I don't have to worry about any of that. So I can use a low-voltage mag pickup flow meter, install it right here in the field, and I'm good to go. The register, the totalizer in this case, which is connected directly to the flow meter, is able to handle the low voltage peak-to-peak sine wave signals coming out of my flow meter. And because it's not trying to retransmit a 4 to 20, I can get a long life battery powered flow rate totalizer. In the case of the one you see here, the PD6830, it could sit in this application for 7 years before it needs battery change. And all it's going to be doing is lighting up that LCD, reading in those pulses, and displaying the instantaneous rate and the total that I can reset daily for this application. And that means that I have no external power required anywhere. I've got my flow meter and my totalizer essentially freestanding in the field with no conduit running either. Now the flow register, my totalizer, needed to be mounted directly to the flow meter to reduce my noise concerns and eliminate the need for me to go out and buy a preamp that connects to my flow meter that then needs to have power, which means I need a barrier, which means I need conduit, and all of a sudden my cost would add up very quickly. But because I can mount it directly to my flow meter, I minimize the chance I'm going to have a lot of noise pickup. Everything is coupled together, so it's all by default shielded by the housings, which are grounded, and I should be okay from a noise perspective. And when I went out and I selected the PD6830, it'd be important that I verify that my mag pickup flow meter is going to be generating pulses that my PD6830 totalizer is going to be able to accept. In this case, I can tell you the 6830 has a 20 millivolt peak-to-peak pickup for mag flow meters. So long as my flow meter is 20 or higher millivolts peak-to-peak, which in almost all cases they'll be, I'm good to go. So here I have a great example of just a simple application where I can put a freestanding flow meter with a 6830 or any flow totalizer that worked with the flow meter attached to it out in the field for a relatively small cost that gives great visibility into what's happening at that tank feed. Our second example doesn't use flow. It actually uses a rotary encoder. Now, just to give you a brief idea of how the rotary encoder works, you can see here that it has essentially, this is a simplified version of course, an LED, a disk, and a photo sensor. And as the disk spins, being attached to some kind of rotating equipment, it allows the LED to shine through the slots that are in the disk. And as the light from the LED hits the photosensor, it triggers a transistor output, which you can essentially imagine as me flicking a switch closed every time one of those slots passes. So I hit the slot, I close my switch. Once the slot has passed, I open my switch again. In this scenario, I'm using it as part of an auto feed system for a polycarbonate film cutter. And what they're looking to do is use a batch controller to enter my preset length of film I'm trying to cut. And then when I hit the start button on the batch controller, it's going to close my relays that turn on the motor. It's going to feed that film down the line. And the rotary encoder, as it spins, is going to be generating pulses for each certain number of degrees on the rotary encoder disk, which equates to a certain amount of film length metered out. And then those pulses representing film length are going to come back to the batch controller so it can totalize up how much length of film has been fed out so far. Once the batch controller stops the system, in this case an operator is going to go over to a manual cutter. Those often have special safety requirements, like you have to use 2 hands to touch both buttons in order to operate the cutter, etc. So they're often kind of a standalone mechanical component. I certainly could have integrated in with the batch controller, but we're trying to model something that we've seen before here. So the rotary encoder provides transistor output pulses, which as I said was like flicking a switch. So in some way I'm going to have to be driving power through that switch closure in order to generate the pulse. In this case, that can be done with the batch controller. The 6310 has a 24-volt power supply on it that I could use to generate 24-volt pulses through that transistor. But it could be any power supply I happen to have handy, so long as it can be picked up by my pulse input device. So you can see where I would put in my batching amount in terms of length. It would turn on the motor. The rotary encoder would be using the pulses being generated, thanks to the power supply on the batch controller, to meter out or to count how much film has been metered out. And then when the batch controller stops the system, the rotary encoder would stop. I'd stop totalizing, and they're free to go use the cutter to slice out the film. So in summary, what did we look at here? Well, hopefully we gained an understanding of the theory and definitions behind pulse signals. You understand pulse frequency, pulse amplitude, what a pulse signal might look like, and the fact that it's always on or off. We became familiar with those 2 key specifications that describe pulse signals and cause people the most headache: the maximum frequencies and those voltage amplitudes and thresholds. We talked about the pros and cons of pulse signals. And we put it all together with a couple of real-world applications that hopefully show ways that you can use pulse signals that will make sense for you. And Bruce, another question.
Yeah, last question of the day. And then don't leave yet, because we do have the final question and answer section coming up. So if you can vote, how often do you specify digital displays? And don't panic, we're not going to call you on the phone based on this result. We're just looking for some background on the interaction of the audience with digital displays. Show the results on this one as they come in. Do you specify 1 to 2 times a year, 3 to 10 times per year, or at least once a month, or never? Votes are coming in. Feel free to vote. You know, don't forget, at the end of this webinar, we do have a survey. And if you there's several questions, but one is open. So if you find these quizzes and polls irritating, let us know. If you love them, let us know. Let us know your feedback, because we're always trying to improve our webinars. So it looks like about everybody has voted who wants to. Last chance. I'll go ahead and close the poll. There's results, at least once a month. Actually a good spread here. Only 10% never. Okay, good. Thanks everyone for participating with the polls and the quizzes. Hope that made it a little more interesting for you. So, questions and answers. We've got about 5 minutes, and I think we can get a few questions in. We've got a lot in the queue. Lee would like to know, with pulses generated by a spinning magnet, is there a problem with jitter when metering slow-moving flow? And if so, how is that problem dealt with?
Well, ideally there wouldn't be. You hope that whatever your generator is, if it's a flow meter, for example, you would hope that the technology takes that into account, and a high-quality device should be able to read to a very low flow rate without generating so much jitter that it's confusing your signal. That having been said, it can cause problems, and you'll know the flow meters that have those issues when you're looking at their spec and they recommend a minimum flow rate in order to maintain their accuracy. For example, a flow meter is always going to be given a K factor with it. That's the number you enter into your register so that it converts, well, okay, how many pulses per 1 gallon am I generating, and they're going to give you some number. What you'd find is that on those type of devices where jitter becomes a problem, they'll say, well, here's my K factor, but it's only valid above this specific flow rate. And then under that, they may not give you anything, or they may give you some kind of changing nonlinear K factors to try to reduce the effect that jitter has. So most of the time, hopefully, you wouldn't have to worry about that. But if you start seeing specifications that require minimum flow rates, you really ought to start paying attention, because it can be a problem if the device can't handle it mechanically. And unfortunately, there is no good way to deal with it from the receiver side. The receiver doesn't know what the flow rate is. It just reads the pulses. So it's up to the generator, in this case the flow meter itself, to be able to handle that. All right.
Okay. Manny has a question, and there's been a few questions along this theme. The question is, when wiring the 2 wires to measure a pulse signal, what's the max length you can run the wires, assuming noise is not an issue?
Well, assuming noise is not an issue, the maximum length is going to be dependent on your amplitude, the amplitude of the pulses. So if noise isn't an issue, the next biggest concern you're going to have is going to be voltage drop across the wire. And as I mentioned earlier, the resistance of wire is very small. And at that point, you start to have to know more about your application. How much power can the pulse generator actually produce? Can it handle the V equals IR calculation that's required to run over the distance of the wire? For the most part, I think it's safe to say if you needed to run a pulse a couple of 100 feet and you have a good powered pulse, you have no problems. If you want to run at 1,000 feet and you have a nice powered pulse, you don't have an issue. If you want to run a flow meters mag pickup a couple of 100 feet, now you could start running into issues. So unfortunately, it's not going to be something I can easily give an answer to, because you really need to see the specifications of the pulse generator to know. But it has to do with if noise isn't your issue, it's going to have to do with the resistance of your wire, and can your pulse generator handle that, and is the voltage drop across that wire going to start interfering with your signal at the receiver? In most cases with a powered output, your answer is going to be no, but I can't tell you specifics without knowing more about your specific application. If you have one of those in mind, feel free to let us know, and we can talk to you about it a little more after the webinar. All right. Looks like Bruce has lost his connection. So I'm going to move on and wrap us up here, seeing as it is 2 o'clock and we don't want to keep you over anymore. We will do our best to get back to you with any questions we didn't answer. And if there's anything else you have for specific questions, feel free to type it in now before we give our wrap-up. Hopefully we'll see you at our next webinar, which is February 17th. And the topic of that webinar is the trouble with ground loops. I'm sure that all of you are familiar with the infamous 4 to 20 milliamp ground loop, and that it can cause you a problem. And the purpose of this webinar is to discuss really what those are and how to avoid them. This webinar is going to cover both true ground loops, meaning those that are caused by, for example, not having single point grounds, as well as wiring issues to multiple input devices like PLCs and multiple input displays that can be caused by shared commons in 4 to 20 milliamp systems. So if you ever ran into a situation where you hear about ground loops and it's causing you a problem, this is definitely a webinar for you. All of us here today represent Precision Digital, a manufacturer, supplier, and servicer of digital instrumentation and displays for hazardous and safe areas. Hopefully we're your choice of source for pulse input meters and controllers, but also loop-powered meters, digital panel meters, explosion-proof instruments, large display meters, annunciators, and more. With that, I want to thank you on behalf of myself, Bruce, and Ryan. Our contact information is here on display if there's anything else you'd like to follow up with us on. And hopefully we will see you at our next webinar on February 17th. Thank you.